Hello, thank you all for coming to our talk about the birth of SemGrip Pro, or how we implemented interfile analysis to find the vulnerabilities that matter. So, quick recap. SemGrep is a fast open source static analysis tool for improving code security. And we also have a pro version with more powerful analysis that specializes in detecting vulnerabilities. If you didn't know about that and you're interested, I'm sure our salespeople would be happy to talk to you. But during this talk, we're just going to tell you what it is, why we built it, and how it was a different challenge than we expected. So I'm Emma. I've been a software engineer at SemGroup for 3 years. I started working on interfile analysis back when we gave it to our first users to try. And then with Colleen, I co-led the project that became the SemGroup Pro engine.
And I'm Colleen. I'm currently a security engineer at Vanta, and I was previously at SemGroup. I was there for around 3 years and co-led the project with Emma that became the SemGroup Pro engine. And you can find me at ChaiDai on Twitter.
So let's start off with a question. Do you use SemGroup more often to eradicate bug classes or to find high priority vulnerabilities? Feel free to put your answer in the chat or just like think it to yourself. Yeah, so I see some people saying high priority vulnerabilities. So if you said that, you're definitely not alone. Because of the customizability of SemGrep, it's really easy to modify existing rules or write your own rules to look for vulnerabilities specific to your code base. But that actually wasn't what SemGrep was designed for. When we designed SemGrep, we were imagining it as a tool to help people eradicate entire bug classes by enforcing like secure patterns over insecure patterns. Um, and so because people were using it to find vulnerabilities, we would get a lot of feature requests around that. Maybe some people would say, hey, this rule has a lot of false positives, more vague. Or some people would use it would talk about it more specifically. They would say, hey, we have these constants that are being flagged as not constant because they're defined in a separate file. Or we have this input in a separate file that can reach this insecure package and we'd like insecure call and we'd like to trace that. So with all of these feature requests, we knew that this was something people really needed, but we were a little bit torn because we had our original philosophy and we wanted to keep SemGrep really, really fast to help people with that purpose. So what we decided to do was create a new engine specialized for that use case of finding vulnerabilities. So that's the SemGrep Pro engine. It was designed to be more powerful analysis with the focus on finding high priority vulnerabilities for people. Like we discussed, this was created in response to strong user demand, which means that while there was going to be like some engineering challenge with the making interfile analysis work, it should have been easy to know what to make, right? Yeah, so that wasn't quite true. Um, while we knew that we wanted more powerful analysis, that in itself is a hard and more importantly, a vague problem. Previously with SemGroup development, we would often just gather some use cases, design a feature for it, try it out, get some feedback, and just iterate. And that worked really well. But for interfile analysis, we didn't even know what exactly we needed to build. It wasn't enough to just start from the features that we thought we needed to build. We needed to first go back and figure out what the correct features were. So that's what we're going to talk about today. As a quick outline, we're going to start off going over the SemGrep philosophy and going over some terminology that we'll need later. We'll talk about why we made the SemGrep Pro engine in more detail. We'll tell you about our first attempt, Deep SemGrep. Then our second attempt, when we went back to the basics to understand the problem space and communicate to our vision to our customers. And then we'll tell you about whether or not it worked.
So let's talk a little bit about subgroup philosophy and terminology. So originally, as Emma was saying, subgroup was focused on this concept of flagging insecure functions and some widely used insecure patterns. So we were really focused on this concept of secure defaults. You might have heard it being talked about in the security community as part of a more modern way of looking at security. And the true premise behind secure defaults is that we want to make it easier for developers to do the right thing. Um, and by doing this, the premise is that we can eliminate entire vulnerability classes as a whole and free up time to do other things. As a good example, maybe we have a React app that potentially has a few dangerously set inner HTML calls. And if we can just eliminate all those calls, we aren't so worried about cross-site scripting anymore. So SemGrup's original philosophy was to really just broadly flag on insecure functions, such as dangerously set inner HTML and other functions like that. So here's an example of a secure defaults rule that we wrote in the past. So let's take a brief look at this. And if we look at this, we see that this is the SemGrep playground. And on the right half of it is some test code that we've inputted. And on the left half is our simple editor that essentially tries to match things on the right. So let's take a look at this rule, the test code, and what we're trying to catch with it. So if we take a look at the test code first, we see that this is some Java Spring code. And what we're doing over here is we're taking in some inputs via request param string input, and then we're building this process builder. And finally, we're executing a process builder.command with this user input. So this code is vulnerable to command injection because this input is directly going into the process builder.commands call, essentially. So the user can really instruct this process builder.commands call to really do whatever it wants to. Um, and if we look over here, this is an example of a secure defaults rule that wants to catch cases of this process builder dot commands call and capture cases where we're just using this because for one, why are we using this function that normally people don't use very much? And we want to just be aware of these cases because it's potentially vulnerable. So over here, what this does is that it just captures a process builder dot commands function call. So this is an example of a secure defaults rule. Awesome. So because we were very invested in this original SemGrep philosophy, our engine really developed to match this philosophy. So a lot of secure defaults rules where we're matching calls to insecure functions and widely used insecure function patterns don't really need interfile analysis. This is because, like in the example above, we're looking for a specific function call or maybe a specific parameter that hasn't been set. So instead, we focused on very fast within the file analysis. SemGroup originally only did analysis within the file. However, what we learned over the years is that even if security teams really believe in secure defaults, it's really oftentimes not easy to achieve. A lot of times it's an ideal that we want to get to, but our security teams are so overloaded with things that come in. There's not enough time to really eliminate all these insecure patterns. So a lot of insecure or secure default rules alerted at the site of a function, like the example we saw before, and this led to a lot of alerts that might not necessarily need to get fixed immediately. And of course, if you've ever worked on a security team, you know that these alerts sometimes get put on a backlog that people don't really look at because ultimately we want to make sure that the critical and high vulnerabilities are fixed, and we'll deal with the other ones later. And especially for secure default rules that alert at the site of a function and things that aren't specifically critical vulnerabilities, this can lead to a lot of alert fatigue, especially if your team is already swimming in potential vulnerabilities to actually remediate. So instead, what a lot of security teams find helpful is to alert less on code that um, that is not necessarily high priority and instead alert more on things that look like a high priority vulnerability. And this leads to less alert fatigue and more fixing of these problems that security teams want to solve. So you might ask, how can we flag on mostly high priority vulnerabilities? Well, we can do so with the help of taint analysis. So let's talk a little bit about taint analysis. So in order to really understand why taint analysis is valuable, let's talk a little bit about how vulnerabilities really look like. And a lot of cases, vulnerabilities sort of look like this. There's some user input that somehow enters a potentially dangerous function after passing through a bunch of variables or string concatenations, etc. And this is an example of something that's a good use case for taint analysis to catch. So if you take a look at this theoretical example, there's some user input, and then it goes into some variable or some intermediary state, and then ultimately enters into a dangerous function. So what taint analysis does is it allows you to mark something as potential user input as a source of taint. So if this potential user input is then assigned to another variable, it marks that variable as tainted. And if a tainted variable enters a function that would be dangerous if user input entered it, SEMGRUP will alert or taint analysis will flag. Um, but in taint terminology, we don't really talk about user input entering functions. We talk about sources entering sinks. So sources are usually sources of user inputs or sources of potentially dangerous things. For example, URL parameters, cookies, data from a third-party service, etc. And sinks are functions that are dangerous if user input gets passed into them. So this could be a unparameterized SQL query. It could be a shell exec call. It could be a process builder.commands call, as we saw in our last example. It could be a lot of things. So ultimately what taint analysis does is it sees whether a taint source will ultimately go into a taint sink. So we talked a little bit about how it works in theory, but let's apply this to sort of an actual code example. So again, this is some Java Spring codes, and we see that it's very similar to the test code we saw before. Um, so we have this string input that is getting concatenated to this string commands string. And ultimately, command is passed into this process builder dot commands call over here. So what would be the source and the sink in this example? Well, the source is where the input user input enters. So this would be the request param string inputs. And the sink is where the input is dangerous. So this is the process builder dot commands call. So now let's quickly see how SEMGRUP can use taint analysis to catch this code example. So on our right, we have the code that we were looking at previously with this request param string inputs, and then this process builder being built, and then this command being equal to some string constants plus the user input, and then this process builder dot commands call being called over here. And this is an example of a taint rule that SEMGRUP can be used to write. And over here, we see that we can specify the mode. So the mode is taint. And over here, we can specify specific sources and specific sinks. So over here, we want to make sure that we just specify a source as just a request param input. And then over here, our sink is this process builder dot commands call. So if we run this, we see that we're getting this, and we know that user input is going into this command. So this can really eliminate vulnerability or eliminate false positives. Oops. Okay. So some people might be thinking, it seems like a lot of security issues are essentially data flow issues. And this is very much true. Awesome. So now that we've talked a little bit about our backgrounds, let's talk about why we made the SEMGRUP Pro engine and why this is so important to finding these high priority vulnerabilities and eliminating false positives. So, as we said before, SemGrub was originally made with secure defaults in mind, and therefore it was only made within a file analysis. So this was true for our taint analysis too. It only works within a file. But a lot of dangerous vulnerable code often crosses the file boundary. Um, you might see code like this, right? What if the previous example was split into two files? This is pretty common, and a lot of vulnerable code is split into 4 or 5, maybe more files. So over here, we see that this is our source, and we're returning test2.test2. And test2 over here is the function that builds this process builder, and then later calls process builder.command. But because SemGrep previously didn't do interfile analysis, it only analyzed things within the file, SemGrep wouldn't catch this because this crosses the file boundary. And of course, if you are working in security, you know that a lot of your vulnerabilities do cross the file boundary, and it's very valuable to have analysis that does and do indeed see multiple files. So ultimately, interfile analysis lets us connect this call and really lets us find these types of vulnerabilities. So what it does is we can see that this is a source, and we can connect this test2.test2 with this function below. Ultimately, we needed interfile analysis, and this is just an example of the process builder.commands being found when we're splitting this test code across two files. So ultimately, we made the Pro engine because we needed movement from broad flagging of insecure functions to high confidence vulnerability catching. And we needed more tool precision. We ultimately wanted to reduce alerts on what is vulnerable and alert on vulnerable cases we were not catching before. We also recognize the need for sort of a balance between catching too many things, and also sort of this visibility problem that security engineers have. So with the secure defaults problem, there was a lot of alerts and you could see a lot of parts of your code, but there was too much alerts and this caused a lot of alert fatigue ultimately. So we wanted to make sure that we struck a balance between having these alerts on vulnerable cases we were not catching before and sort of reducing false positives. And I'll pass it to Emma to talk a little bit about SemGrip Pro development.
Yeah. So now that we've gone over what the SemGrip Pro engine is and what we hoped it would do for you, um, it's time to start talking about working on it. So I put up a timeline here. The point of this is mostly just to show progression, but it's now November 2021 and we're starting work. Back one slide. So like I discussed, the way that we've often worked on these features is we'll sit down and we'll figure out what we want to build first. So it's the same thing here. Two of my teammates, Yoan and Yago, who are both really awesome, set out to make a proof of concept about how we could extend SemGrep using interfile analysis. So they worked on this, they got to work on some basic cases, and then they kind of brought the rest of the team in to extend it. When we built this proof of concept, we focused on Java because it's a nice, well-behaved language. So we called this Deep SemGrep. So in creating Deep SemGrep, we were starting from the features. So the way that we thought about this was we identified the features that would benefit the most from interfile analysis. So definitely, as Colleen talked about, taint analysis was really high on that list. But there are also some other features which were really important. One of them was type inference. Since type inference is something that really benefits a lot from being able to look at multiple files. Most of the time, if you define a type in one file, you might use it in that file, but you'll probably use it all over the code base. And the same thing with constant propagation. Constants defined in one file might be used in many other places. And so we figured, okay, if we can lift these features, make these work across files, then we'll be able to get a huge lift compared to SemGrep. So we made this, and then as we do, we demoed it to customers or to just like SemGrep users so they could tell us what to do next. Yeah, so it was around February 2022 when we started reaching out to our first customers. We were very optimistic at this point. Um, and at so what did our customers say? First of all, we have awesome users. Most people we reached out to gave us examples. If you have ever given us examples, thank you so much. We really appreciate all of the help that we've gotten and the feedback in making our engine better. Um, so most of our customers would give us like 3 to 10 cases. Um, and these cases would have two types usually. So one, sometimes there would be a case that SemGroup could already match. Maybe like when they wrote the rule, there was some feature they weren't aware of in SemGroup that they could use, but we would be able to help them write a rule to match it. And then the other type was an adapted realistic snippet. Naturally, most of these users weren't giving us their full repos, right? Especially if they were working at a company. You can't just share your entire repository with someone else. So they would take snippets out to illustrate what they wanted to match. And oftentimes they would minimize, and sometimes they would make it a little more complex, or not quite complex, but they would change it to test this hypothetical scenario that they were curious if we could match. And so these could become very difficult because people would add like things that they were wondering if we would match or not. So here's an example to illustrate one kind of realistic difficult snippet we'd get. Imagine you have 3 files. They don't have to be necessarily 3 files, but let's say they are. So in file 1, we have some source, some user input in Java. In file 2, we have an external service that's written in Python. And then in file 3, we're in Java again. And so we want to match when our source, our user input, reaches our sink. But we also want some specific state to be true of the external service. So cases like this are really interesting to us. It's something that we do want to support, but they weren't what we were looking for our V0. We wanted to stick to just one language there. And so if we got a test case like this wouldn't be super helpful to us because we didn't want to focus on it yet. The next thing we would get is we might get something like, okay, so file 1, we have the source, the user input again. It's put into a hash table. And then later, it's taken out of the hash table and put into the sink. And so this is a really straightforward example, but it would raise a lot of questions actually, because remember, we're getting minimized examples. We know that. And so we would have questions like, okay, in the real code, would that source get modified before being like after being put into the table? Would the values in the table get shuffled at any point? Like we weren't able to see that because we had minimized examples. And that can really change the difficulty. If the values, like if to figure out whether the source makes it into the sink, we have to trace a loop and figure out like how many iterations it'll go through, something like that. That becomes a really difficult problem. So next slide. So in all this, it turned out that while we got a lot of examples to start, by the end, the number of examples that really helped us, that we really could like develop off, wasn't that many. To give like an illustration with like vague numbers, like imagine we had 50 total examples, maybe 30 of them would be possible using like SemGrip OSS engine, which actually made us wonder like, is the better thing to do just to improve the usability of SemGrip OSS? And then of the new examples, maybe like half of them wouldn't be in scope. And then the remaining, there would be some that would be already possible, some that would be possible with a lot of work, and some that would raise questions that would suggest maybe a lot of work, but maybe not so much. And it was hard for us to prioritize these. So how do we prioritize them? We needed to get more examples so we could see which case was most common. And to do that, we needed more users. So accordingly, in May of 2022, we launched the Deep SemGrip private beta. If you were around for this, if you've been with us for a while, you might remember this blog post introducing Deep SemGrip from our CEO, Isaac Evans. We advertised what we had, so that we could get people interested and get ideally users who were interested in working with us to as a development partner to give us more examples. And so we had tons of interest. People are really excited about interfile analysis, and they gave us they had repos including Ruby repos and Python and JavaScript and PHP and C++ across all the languages. The problem was this didn't actually help us because we only supported Java. And so we could only it was only useful if people had Java repos. But then oftentimes people would have we would get like people who had Ruby repos be like really interested in working with us. And so what would happen is we would start saying, okay, that we're focused on Java, but like we need examples and we can get some Ruby examples. So let's implement some Ruby. And then inevitably, people have shifting priorities, people have other things that they need to do. So maybe we wouldn't be able to get many more examples from Ruby, and they would be like of a different nature. And so someone else would come with Python and be interested. And we'd say, okay, well, we have some basic Python support. We can like start with that and get examples. And you see where this is going. We were just getting distracted, trying to chase people who would give us examples. And we weren't making progress. So the fundamental problem, I think, is everyone wants interfile analysis, but that doesn't mean that they can tell us what problems we should be building for. Security professionals aren't program analysis experts. They shouldn't be. That's what we're here for. And even more fundamentally, the problem was that interfile analysis is impossible, actually. Specifically, perfect program analysis is impossible. You've heard of like the halting problem or Rice's theorem. You're familiar with the idea that there are some properties, in fact, almost all properties of programs cannot be decided for all programs. So you can't just take any program and ask, you can't write a thing to take any program and ask a question about it, and it will always give you the correct answer. So to attempt to do this, all program analysis tools will approximate. And depending on the approximations you can you can be very fast or you can be slow. You can take hours, days. You could become unusably slow very easily. And the one thing we do not want to be is unusably slow. We've always believed that the most important thing about a security tool is that developers are happy to use it, which means we need to be able to iterate quickly. We need to be able to get it in CI flows. So figuring this out for interfile analysis was really hard. You might ask like, oh, what's so special? Like you've already done program analysis with SemGrep. Like, why is it harder now? But with SemGrep, we had restricted our scope really clearly so that we could solve our problem well. We said we are not going to cross file boundaries. We'll do pretty much, we will do most things within it as long as they're related to security. But since we won't cross file boundaries, that really made it easy to stay fast. Now we were trying to break that barrier. We're trying to say, okay, we are ready to expand to anything inside your repo. But that's a really broad scope. So we needed to figure out how to draw a new boundary so that we could stay within it, but still solve these problems that our users were facing. So to do this, we started the benchmark.
Awesome. So now that we've talked a little bit about the private beta and the initial building of Deep SemGrep, let's talk about what we did next, which is starting a benchmark. So as Emma was saying, we were getting all these requests for interfile analysis. However, as we talked about before, this truly didn't mean that customers could really tell us what to build or what direction to build in. And what customers didn't actually want was interfile analysis. As a security engineer, all you really care about is better results, less false positives, more alerting on things that are critical vulnerabilities, etc. And a lot of people didn't really care how we built or what we built as long as it led to better results for them. But this still didn't mean that customers could really tell us what direction to build on and what features to really focus on. So instead, we took this in our own hands. We built a benchmark of vulnerabilities from a lot of GitHub open source repositories. But we couldn't actually theoretically build a benchmark of 100,000 repositories, which are the amount of GitHub Java repositories that exist. That would be humanly impossible. So we instead chose to really downscope it to Java and select a specific type of vulnerability. And we chose SQL injection. Um, and Java code usually has very long stack traces because every class has its own file. So this was really good for collecting interfile analysis examples. And of course, we had started building interfile analysis in Java already. And we chose SQL injection because it's relatively uniform. It looks pretty similar in most code bases, and it's also pretty reflective of injection type vulnerabilities, which people want to catch, and there are a lot of. So let's talk a little bit about how we started creating this benchmark to really help us build in the direction that we wanted to. We chose four sources to gather repositories from for a benchmark, and three of these were for gathering cases where we weren't catching something we should catch. So these three sources were historical CVEs from the MVD database, GitHub commits with comments like fix SQL injection in the commit message, and some purposely vulnerable repositories like Fullnado, and other things. Only one of these sources was for gathering cases where we were catching something we shouldn't. And this was a false positive scanner where we ran SemGrep on a bunch of open source repositories and filtered through the results to see whether we caught something we shouldn't have. So ultimately, in creating the benchmark, we went through three primary steps. We needed to collect these repositories from our different sources. And of course, when you're creating these repositories, what is the most important part is making sure that the data and the repositories you're collecting are good. So we really wanted to focus, and we really focused on this step of collecting good repositories to build from. And the second step was to write some group rules to see what we were catching currently and what we wanted to catch. And the third step was to label the sources and sinks in order to make sure that we were doing our interfile analysis properly. So the first step we took to craft our benchmark was to gather our repositories. We filtered through a lot of GitHub repositories, around 1,000, and gathered ones with Java SQL injection vulnerabilities. And we looked at all these historical CVEs in order to gather some more complex examples. As you know, the repositories in GitHub are very unique. Some of them are a lot simpler, some of them are a lot more complex and widely used. We wanted to look at the historical CVEs because a lot of these were open source GitHub repositories that were widely in use and pretty complex. We also took some historical GitHub commits with messages like fix, SQL injection, and some purposely vulnerable repositories. We wanted to have access to all these sources because we wanted a wide variety of repositories, repositories that really could reflect different types of code. And the purposely vulnerable repositories were quite simple and not complex. So they were good for initial development. And things like the historical CVEs were pretty complex. And this gave us a wide array of things to look at. And of course, we also looked at repositories that some grep SQL injection rules flagged false positives on to make sure that we weren't catching things that we shouldn't catch. Awesome. So after we really did that, we started writing some grep rules. We wanted to do this in order to see whether we caught these vulnerabilities with our current engine and also have sort of a some sort of comparison between the open source rules and the open source engine as compared to our interfile rules and interfile engine. We also wrote some basic subgrep rules to test how powerful the interfile analysis actually was. And the last step in this process was to trace our vulnerabilities from sinks to sources. We would usually be given the PR of the fix, and it was usually closer to the sink. So we would have to really trace where user input could possibly lead to a vulnerability, or how this user inputs could actually get into the sink. Honestly, this was quite difficult in the sense that Java's call stacks are pretty complex if you've ever looked at Java call stacks. So in order to actually find the SQL injection vulnerability, you might go through all of these things. So there might be some like JDBC calls, there might be some things built on top of it, like the DAO, and then there's business logic, and then maybe user input comes from some Spring Webflow or something on top of that. So ultimately, we were going through all of these files and all of these areas, and none of these function calls were actually named the same thing. So tracing something from sink to source was very much not easy.
But despite, oh, sorry. Yeah.
No, go ahead.
But despite all of that complexity, Colleen finally annotated all of the benchmark. And so we were able to analyze the results. Yeah. So the first question we asked with the benchmark was, how does SemGroup do? And the answer was not well. SemGroup got an overall score of 10% with the rules that Colleen was writing. So to be clear, this can vary a little bit based on the rules because you could write rules that were more specialized for SemGroup, which would cause more false positives, but would allow it to catch more things. But it did not do better on those either. So we'll stick to talking about these high precision rules. So using these, SemGroup was able to catch only 3 of the vulnerabilities. It missed 27 vulnerabilities, and it did at least not get any false positives. So now that we had looked at how SemGroup did, we were able to say, yeah, we want to be able to do a lot better. We want to be able to catch at least half of the vulnerabilities that we're seeing from these real repositories from the CVEs. And so to answer what we needed to change, we needed to figure out for each vulnerability we want to catch, what are the code operations we would need to understand to be able to have found that vulnerability. And so this was kind of a moment of truth. There was a really big question of, will this even be feasible within like the time limits we were setting for ourselves? So there were some things we were really worried about finding. One thing was frequent modification with tainted value. That's kind of what I was talking about, like with the hash table, like what if it was being modified in a for loop and we needed to understand that for loop. We were also worried about using like dynamic Java features like reflection in like these critical pathing vulnerabilities. What we actually found was none of that. It turned out that the existing interfile engine was pretty good, solid already, but there were some things that it needed to handle better. So the things that we found really commonly across all of the vulnerabilities classes or the vulnerability sources that Colleen mentioned, including the CVEs that were filed on like these popular open source repos and the GitHub Actions repos where we found commits like fix vulnerability. Among those, what they basically did was they would often pass a tainted value unchanged through many functions. That was great to see because the key there is that it was unchanged. They would also use OOP best practices we didn't support yet, like getters and setters and inheritance, but this was really simple to add. And they would indeed put tainted values into collections, but what we were really worried about, the frequent modification, didn't happen. And so this meant that what we were hoping for, interfile analysis that was actually useful, that would actually find vulnerabilities in the wild, was definitely feasible. So we did it. We implemented each of the fixes that I mentioned on the previous slide. I made some more changes as well. And afterwards, when we ran the benchmark a second time, we got to a score of 56%. So this time we found more vulnerabilities than we missed using the interfile engine. And we didn't have any more false positives than before. So now that we did that, we were ready to re-engage with customers.
Yeah, so how did it feel reaching out to customers the second time? After we had a working product with decent interfile analysis, customers actually responded very much differently and with better feedback than they did after the first reach out. So this led to a lot of one-on-ones, a lot of demos, a lot of code examples like why didn't SemGrep catch X, Y, or Z, and lots of useful feedback. So this meant that we had substantial improvements that people could understand and use, and customers were a lot more willing to work with us because of this. And because of this, there was a lot more feedback from customers that we could build upon, and this meant that we had valuable feedback. So we must be ready to launch, right? Well, not quite. We had created some new interfile rules, had selected previous rules, and had also built out our interfile analysis, but we needed to ensure that the user had a good interfile analysis experience. And this included things like supporting earlier versions, making sure that SemGrep Pro was running quickly, making sure that there was a good onboarding experience and good onboarding UI, etc. So once we tackled those issues and solved for those, we were ready to launch. So it was finally time to launch. We launched the SemGrep Pro engine with advanced code analysis and interfile capabilities on February of 2023.
Yeah. So how did it end up going? Overall, we are really pleased with how the SemGrep Pro engine did. Actually, before we even launched the SemGrep Pro engine, there were 3 CVEs filed that were discovered using it. It's been almost a year, almost exactly a year since we launched. And we have close to 100,000 scans per day. It's really grown over time. We also scan a lot. We also support a lot more languages. When we started this, we were just using Java, but now we support JavaScript, Go, C#, and Kotlin as well. So a lot of more people can benefit from interfile analysis. So some takeaways. One, we've learned that program analysis is hard. We've learned that figuring out what security people desire from a static analysis tool is hard. It's hard to pinpoint what exactly you need to solve vulnerability detection problems. And we've really come to understand that that's our job to figure out what will allow us to give you the best results, what we need to support without making our product impossible to use. We've also really learned the importance of being able to communicate what benefits you have. It was much easier to get people engaged once they saw, oh, here are the things that you support, instead of us just throwing them a tool and saying, hey, does it catch your things? So obviously, we are not done with the SemGrep Pro engine. There's so much more we want to do. We would love to support every major language, depending on how quickly major languages are added to the ecosystem. That might be a difficult goal, but that's definitely where we want to be. We also want to understand more frameworks. We've realized that it's even more important that we're able to understand frameworks, not just languages, because frameworks can often affect how data flows among files, and we need to be able to track that. We want to keep improving performance. Right now, our P95 is pretty good. I think it's around 10 minutes or less. I think it's less than that. I don't quite remember, but we want to get it faster than that. We want to be able to scan even like large repos under 10 minutes, because we think it's just so important to developer usability. And we're always looking for even more advanced understanding. There's always more stuff that we want to be able to follow. So that's the end of our presentation. Thank you so much for listening.